In this lesson, we have an example of the type of problem solving that we will be doing in this chapter. Now, I have right up here at the top, and I know it's written kind of small, but it is important that there are basically two approaches now that we have to problem solving. One is going to be to use Newton's second law, namely Newton's second law for torques and Newton's second law for forces, and we're going to always do that if we're being asked to solve for the acceleration tangential or the acceleration rotational alpha. Now, if all we are being asked to solve for is the final velocity that a system has that incorporates both rotations and translations, then the energy approach will often be better. For us right now, you will be told whether to use Newton's second law or whether to use energy to problem solve the problem. And if you are told which to use, you must use that approach. Well, we have both translation and rotation in this simple machine named after George Atwood. It's a big wheel, a disc, a pulley that has a string wrapped around it and a mass hanging from the string, and as the mass falls, the wheel turns. So we have translational motion of the mass going straight down and rotational motion of the wheel up here. So both have to be analyzed. Now, the big arrow that I have here and the tricky and the highlighted part, please do not just gloss over this. This problem becomes extremely difficult, if not impossible, to solve if you don't realize that the tangential motion on the rim of the wheel has to match the tangential linear motion of the block as it falls, because that's what the string is doing. The string is locking them together. It's coupling this system in a way that's locking that tangential motion on the rim of the wheel with the linear motion of the block falling. So here we are looking for the acceleration of the system, so we're going to use the Newton's second law, sum of the torques and sum of the forces approach. Well, if that's what you're doing, if that's what you're being told to do, as we are here, read the question. So I have here highlighted, underlined, the information we need to calculate the moment of inertia of the wheel. So the block does not have a moment of inertia. It only has linear motion, but the wheel is spinning. The moment of inertia of a solid wheel, we'll see, is 1/2 mr squared. That is one we are going to have to memorize. We know for the point particles, they're mr squared, and so it's not a hard one. When you have point particles going from 0 to capital R, just keep in mind the average is kind of in the middle, 1/2 mr squared. Well, let's take a look at sum of the forces, sum of the torques. All right, first the pulley. So we have the string wrapped around the pulley. We're going to look at sum of the torques equals I alpha for the pulley. Well, there's only one torque. The only torque acting on this pulley is due to the tension pulling straight down, and that is going to cause the rotation of the pulley. Well, torque R cross F. Remember, we're going to use R cross F. We're going to draw them from a common origin. That gives us 90 degrees when we slide the R vector and the T vector together. So that is how we get R times T times sine of 90, and if I use my right hand rule, that's going to be a thumb into the paper. It's a clockwise torque, so it's negative. The moment of inertia we calculated is 0.05, so that's how we have the 0.05. And it is important, so please make sure you get into your notes the importance of using the positive or negative for all of the vector quantities, the torque, the alpha acceleration, the force, and the linear acceleration. So we have our equation using torque equals I alpha as best we can. We have two unknowns, so we don't have a solution to the problem, but we have an equation. Let's box it up. Well, if we look at just the mass falling, we get mg straight down. We get the tension T up. So that's why we have T minus mg equals mass times acceleration. And notice I have to have the negative here because it is down. You will not get the right answer if you don't have that negative in there. Well, I have too many unknowns without my A equals alpha r, so that's why we introduced the A equals alpha r, right? Because I have tension and acceleration. Over here I have tension and alpha. But since we know A equals alpha r, and that links them together, right? So the alpha and the A go together because of our tricky trick up here, right? So because of this guy up here, the alpha, A equals alpha r here, will be the same A that's down here. So I'm going to leave it to you to solve these equations to get the correct answers. Tension is 6 newtons and A is 4.8 meters per second squared. And then once we have the acceleration, we can, of course, use our constant acceleration equations to get the speed that this would have after the block has moved downward, 0.25 meters. But I also have shown here, and please copy it down, look at how easy the calculation would have been if all we were looking for was the final velocity of the block after it fell the 0.25 meters. Well, there's no friction in this problem to lose energy, so we have kinetic plus potential equals kinetic plus potential. We're told that it starts from rest, so that's why the kinetic initial is 0. Our potential energy is mgh just from the block, so the wheel itself does not give us any potential energy. There's no ability of the wheel to put energy into the system. So when the block falls a distance h equals 0 is the lowest most point in the problem. No potential energy, and look what we have here though. We now have both translational and rotational energy in the problem. So the translational energy of the block, right, plus the rotational energy of the spinning pulley has to equal the potential energy that the block had as it's falling. So again, it's locked in place where V equals omega r. So we can relate the V and the omega since that trick of the tangential motion on the rim of the wheel and the tangential motion of the block is the same. The V tan and the omega will now match up. And when you plug in your numbers, this is all you need. We have everything we need to get V final equals the 1.55. So again, for you right now, you don't have to worry about being told which way to solve the problem. The questions themselves will tell you use Newton's second law to problem solve it. And if you're told to use Newton's second law, they don't mean just F equals ma. They now mean F equals ma and torque equals I alpha. Use them both to problem solve the problem and make sure that you get that A equals alpha r into your analysis as well to help you problem solve if they're linked together by this string. So I realize it looks like a lot is going on and more is definitely going on, but I think our new equations and our new understanding of rotations make this all very possible. So I'm going to clean up my erasures, my commenting here, to give you a clean page again if you want to pause to get your notations in there, and we can and will, of course, discuss this in class.